Welcome to the first lesson in our mathematical modeling series. We will begin with equations that may already feel familiar and gradually develop a much more general way of thinking. When a relationship is known, an input can be placed into an equation and an output calculated. In practical modeling, however, the relationship is often unknown. We observe examples of inputs and outputs, choose a family of possible relationships, and determine the parameters that select one member of that family. Our final destination is a powerful structural idea. A complicated function can be represented or approximated by a weighted combination of simpler functions. This same pattern connects elementary straight lines to polynomial models, Taylor expansions, and Fourier series. We will build every piece concretely before introducing compact notation. We will not yet study how to fit parameters to many inconsistent observations. That important question belongs to the next lesson. In mathematics, we often study how one quantity is related to another. Distance traveled may depend on time. The area of a square depends on its side length. The total cost of identical objects depends on how many we buy. We usually call the supplied quantity the input and label it X. We call the associated result the output and label it Y. The arrow from X to Y says that an input is associated with an output. Writing Y equals f of X adds one important idea. F is the rule that performs the association. The letter F does not mean multiplication. It can represent any well-defined rule appropriate to the problem. The letters X and Y are labels rather than laws of nature. In a temperature formula, for example, the input might be C and the output F. The essential object is the relationship. Let us examine three known relationships. If S is the side length of a square and A is its area, then A equals S squared. A side length of 3 produces an area of 9. If a vehicle travels at a constant 60 kilometers per hour, distance d equals 60 times time t. 2 hours produces 120 kilometers. Temperature conversion provides another example. Fahrenheit equals 9/5 of Celsius plus 32. This example reminds us that inputs and outputs need not be named X and Y. In each case, the rule is known. We substitute a permitted input, carry out the stated operations, and obtain the output. This direction, from a known rule and input toward an output, is the forward calculation. Picture a function as an input-output machine. For the rule f of x equals 3x plus 2, an input of 0 produces 2, 1 produces 5, and 2 produces 8. Now pause for a check. What output is associated with x equals 4? Substitute 4 for x. 3 times 4 is 12, and adding 2 gives 14. Here is a second check from the same idea. If y equals 4x minus 1 and x equals 3, then y equals 12 minus 1, which is 11. These examples are elementary, but they establish the direction of reasoning that we will later reverse. A familiar and important relationship is the straight line y equals mx plus c. The quantity x varies, and the equation produces y. The parameter m is the slope. It tells us the change in y associated with a 1-unit increase in x. The parameter c is the vertical intercept, the value of y when x is 0. Consider y equals 2x plus 1. For x values 0, 1, 2, and 3, the outputs are 1, 3, 5, and 7. The same slope and intercept are used for every input. Geometrically, the slope is rise divided by run. Here, moving 1 unit to the right produces a rise of 2. The intercept places the line at y equals 1 when x is 0. Hold the intercept fixed and change the slope. Negative slopes fall from left to right. A slope of 0 gives a horizontal line. Positive slopes rise. The line rotates around its fixed intercept because the rate of change is being altered. Now, hold the slope fixed and change the intercept. The line moves vertically without changing its tilt. This distinction is central. The slope controls the rate of change, while the intercept controls the baseline level. Parameters do not describe one isolated data point. They control the complete relationship that is applied to every input. Choose an input on the horizontal axis. Move vertically to the line, and then horizontally to the output axis. Once the equation and its parameters are known, calculating an output is a forward problem. When the value comes from a model rather than direct measurement, we write y with a hat. Y hat. The hat means predicted or estimated. In the expression y hat equals 7 plus 2.5x, the input is x, the predicted output is y hat, the intercept is 7, and the slope is 2.5. This is our second knowledge check. Identify each role before moving on. The distinction between an observed y and a predicted y hat will become essential when data enter the story. A straight line is only one possible form of relationship. A quadratic can bend. A cubic can change curvature. A sine function repeats. An exponential can grow increasingly rapidly. Watch the same input marker move through these different rules. The input has not changed, but the output changes because the relationship changes. When a function is known, this is still a forward calculation. Substitute the input and evaluate. The difficult practical problem begins when the true function is not supplied. Now reverse the situation. Imagine recording study time and examination score for 5 students. The observed pairs are 1 hour and 52, 2 and 58, 3 and 65, 4 and 71, and 5 and 78. We label the pair for observation I as x sub I, y sub I. In school exercises, the equation is usually given and we calculate y. Here, the examples are given, but the equation is not. We must propose a mathematical form and determine its unknown quantities from observations. This is a simplified illustration, not a causal claim. Study time is not the only influence on examination performance. The example merely gives us a concrete input and output. The observed output is y sub I. It comes from a measurement or recorded dataset. The model-generated output is y hat sub I. It comes from the equation we have chosen. These values may be close, equal, or different. A model is a representation selected for a purpose. It is not automatically the complete true relationship. Pause for knowledge check 3. Explain the difference in your own words. A reliable answer says that y sub I was observed, whereas y hat sub I was calculated by a model for the corresponding input. Plot the observations without drawing a line immediately. What relationship could have produced them? A line is plausible. A gently curving function may also be plausible. With only a few points, many other curves could be made to pass through or near them. The data do not announce one equation. Constructing a model therefore involves a choice about the kinds of relationships we are willing to consider. Suppose we choose the straight line family. We first write y hat equals mx plus c, then transition explicitly to the parameter notation. Y hat equals w0 plus w1x. The correspondence is w0 equals c and w1 equals m. This equation does not describe one particular line until values are selected. It describes the family of all straight lines. 2 plus 3x, 10 minus x, and the constant 5 all belong to this family. The constant function appears when the slope is 0. A model family is the collection of relationships produced by varying the parameters. One particular parameter choice selects one particular model. Imagine a two-dimensional parameter map. One axis records w0, the intercept, and the other records w1, the slope. Every point on this map selects one line in the graph beside it. Moving horizontally changes the intercept. moving vertically changes the slope. This is a conceptual parameter space, a map of possible settings rather than another physical input. Knowledge check 4 asks which expressions belong to the straight line family: 3 plus 2x, 5 minus x, x squared plus 1, and 7. First, second, and fourth belong. The quadratic does not. 7 belongs because it is a line with slope 0. We can demonstrate the reverse problem exactly using two observations with different input values: 1, 52, and 5, 78. Assume the selected line must pass through both points. Substituting the first point into y hat equals w0 plus w1x gives 52 equals w0 plus w1 times 1. The second gives 78 equals w0 plus w1 times 5. Geometrically, forcing a line through the first point leaves many slopes possible. Requiring it to pass through the second point removes that freedom, leaving one line. Subtract the first equation from the second. 78 minus 52 equals 4w1. Therefore, 26 equals 4w1, so w1 equals 6.5. Substitute this into the first equation. 52 equals w0 plus 6.5, giving w0 equals 45.5. The resulting relationship is y hat equals 45.5 plus 6.5x. The slope and intercept were not given in advance. They were determined from the observations under the straight line assumption. 2 points determine one line when their x values differ. With more than 2 observations, the points may not all lie exactly on one line. Finding suitable parameters then requires a systematic fitting method, which we deliberately postpone to a later lesson. Selecting the first and last observations is not a general fitting rule. Certainly, this subscript I identifies an observation. The input x sub I changes from one observation to another, and the corresponding prediction changes with it. The parameters w0 and w1 are shared. They define the common rule applied to every observation. It would be a mistake to assign unrelated slope and intercept values to each row while still claiming to use one line. Inputs vary between observations. Parameters define the model. Consider the observations 1, 2, 2, 4, and 3, 6. The simple line, f of x equals 2x, passes through all three. Now define g sub alpha of x as 2x plus alpha times x minus 1, x minus 2, x minus 3. At x equal to 1, 2, or 3, one factor in that product is 0. The entire added term vanishes regardless of alpha. Therefore, every member of this infinite family passes through the same 3 observations. As alpha changes, the curve can bend dramatically between and outside the observed inputs while leaving the observed points untouched. This is not a trick. It exposes a fundamental limitation of finite data. Observations constrain a function at recorded locations, but do not uniquely specify its behavior everywhere. Because finite observations are compatible with many functions, model construction requires assumptions. A straight line family assumes a constant rate of change. A quadratic permits one controlled form of curvature. A periodic family permits repeating behavior. Localized building blocks can represent effects concentrated near selected locations. More flexibility is not automatically better. Complexity changes what the model can express between observations and beyond the observed range. Data help determine parameters within a chosen family, but the family determines what kinds of explanations are possible. Knowledge check 9 asks why 3 observations do not determine the function everywhere. The answer is that infinitely many functions can agree at those 3 inputs while differing elsewhere. A house price model may use floor area x1 and age x2 to predict price y. Choose y hat equals w0 plus w1 times x1 plus w2 times x2. Suppose the parameters are 50, 2, and negative 1.5, with price measured in thousands of dollars. For a floor area of 100 and an age of 10, the prediction is 50 plus 2 times 100 minus 1.5 times 10. The three contributions are a baseline of 50, an area contribution of 200, and an age contribution of negative 15. Their sum is 235, meaning $235,000. Coefficient interpretations depend on units and describe changes while holding the other inputs fixed. They should not automatically be interpreted as causal effects. With two inputs, the graph needs three axes. Floor area lies along x1, age along x2, and predicted price rises vertically. The equation forms a plane. Increasing W0 shifts the whole plane vertically. Changing W1 alters its tilt along the area direction. Changing W2 alters its tilt along the age direction. Select one house on the input floor and move vertically to the plane to read the model prediction. The third dimension represents the output. It is not decorative depth. For D inputs, expand the model as W0 plus W1 x1, W2 x2, continuing through WD xd. The summation form says exactly the same thing more compactly. W0 plus the sum from j equals 1 to d of W sub j x sub j. The index j labels an input and its coefficient. Knowledge check 5. In y hat equals ken plus 3x1 minus 2x2, let x1 equal 4 and x2 equal 5. The result is 10 plus 12 minus 10, which equals 12. Vector notation compresses a calculation we already understand. Stack x1 and x2 into the input vector x. Stack w1 and w2 into the weight vector w. W transpose x pairs corresponding components, multiplies them, and adds the products. W1 x1 plus W2 x2. The original model therefore becomes y hat equals W0 plus W transpose x. The superscript transpose turns the displayed column of weights into the orientation needed for this dot product. Nothing magical has happened. We have packaged the same expanded calculation. Define an additional input, x0 equal to 1. Stack 1, x1, and x2 into an augmented input vector, and stack w0, w1, and w2 into the matching weight vector. Their dot product is w0 times 1 plus the remaining contributions. The constant 1 allows the intercept to participate in the same multiplication as the other terms. Once this convention is understood, writers often omit the tildes and write simply y hat equals W transpose x, with the first component of x understood to be 1. Now, evaluate the same model for many observations. For observation I, x sub I1 is its first input, and x sub I2 its second. Stack one observation per row. The first column contains 1s for the intercept. The next columns contain the two inputs. Stack the shared parameters into W, and the predictions into y hat vector. Matrix multiplication produces y hat equals xw. Every row is one observation, every column is one input or feature. The parameter vector contains one weight per column. Matrix notation does not introduce a different model, it applies the same model to all rows at once. Focus on the first row. Multiplying it by w produces the first prediction. The same parameter vector then moves across the second row, the third, and every remaining observation. If there are n observations and 3 columns including the intercept, x has n rows and 3 columns. Knowledge check 7 asks 2 questions. What does a row represent? 1 observation. What does a column represent? 1 selected input, or feature across all observations. Repeat this distinction whenever matrix notation begins to feel abstract. Consider fuel use versus speed. The observations fall from speed 20 to 60, then rise toward 100. No amount of tilting or vertically shifting a straight line creates this U-shaped pattern. Introduce the model y hat equals w0 plus w1x plus w2x squared. The x squared term allows the rate of change to vary with x, so the model family can curve. We are not yet claiming this is the best model. We are showing that changing the chosen representation changes the shapes that become possible. Take the concrete model, y hat equals 2 plus 3x minus 1/2 x squared. Separate it into three component graphs, the constant 2, the line 3x, and the downward quadratic negative 1/2 x squared. Add their vertical values at each input to produce the final curve. At x equals 1, the prediction is 2 plus 3 minus 1/2, or 4.5. At x equals 2, it is 2 plus 6 minus 2, or 6. At x equals 3, it is 2 plus 9 minus 4.5, or 6.5. These are required numerical examples that we will soon express with features and a matrix. The quadratic model is nonlinear as a function of x because its graph can curve, yet it is linear in the parameters w0, w1, and w2. Each parameter multiplies a selected quantity, and the contributions are added. Define phi0 of x as 1, phi1 as x, and phi2 as x squared. The model is a weighted sum of these functions. This resolves a common misconception. A model may be curved in the raw input while remaining a linear combination of chosen features. Here, linear in the parameters does not mean a straight graph. A feature mapping takes one raw input and constructs several useful quantities from it. For the quadratic model, x maps to the vector 1, x squared. We call this vector phi of x. A point moving along the original number line traces a curved path when represented by x and x squared in feature space. This space is a mathematical representation, not necessarily a physical place. The model then computes W transpose phi of x. First construct the representation, then weight and combine its components. We can now name the building blocks. The straight line model uses 1 and x. A quadratic adds x squared. A cubic adds x cubed. A periodic model may use 1, sine x, and cosine x. A mixed model may include x squared, sine x, and e to the negative x. These selected functions are called features or basis functions in this introductory setting. Strictly, the word basis has additional independence and spanning requirements in linear algebra. Here, we use the term for chosen functional building blocks, without claiming every arbitrary collection is a formal mathematical basis. Imagine each basis function as one channel on a mixing console. Phi sub j creates a particular shape. The weight W sub j raises, lowers, or reverses that channel's contribution. Adding the weighted channels produces the final prediction. Only now do we introduce the compact general notation, y hat of x equals the sum from j equals 0 to p of W sub j times phi sub j of x. With several raw inputs, replace x by the vector x. Knowledge check 6, in y hat equals w0 plus w1x plus w2x squared plus w3 sine x, the basis functions are 1, x squared, and sine x. With two raw inputs, possible basis functions include 1, x2, their squares, and the product x1 times x2. If x1 equals 2 and x2 equals 3, the interaction feature equals 6. The product allows the contribution associated with one input to vary with the level of the other. It does not by itself prove a causal interaction. It expands the shapes the model can represent. Begin with the plane from the constant and two raw inputs. Add x1 squared, and the surface curves along the x1 direction. Add x2 squared, and curvature appears in the other direction, producing a bowl or dome depending on the signs. Add x1, x2, and the surface can twist. Each visual change is connected to one new term in the equation. The family becomes more expressive because the representation has been enriched. Apply the feature map to every observation. For observation I, construct the vector of basis function values phi0 through phi-p. Stack the transposed feature vectors as rows of the matrix called capital Phi. Entry ij is the value of feature j for observation I. The prediction vector is capital Phi times w. This is the design matrix, also called the feature matrix. It records the chosen mathematical description of every observation. Rows are observations, columns are selected features, and the shared weight vector acts across every row. Return to the model 2 plus 3x minus 1/2 x squared at x equal to 1, 2, and 3. Each raw input becomes a row containing 1, x, and x squared. The design matrix is rows 1, 1, 1, 1, 2, 4, and 1, 3, 9. Multiply by the weight vector 2, 3, negative 1/2. The results are 4.5, 6, and 6.5. The same values obtained by direct substitution. Matrix notation has organized repeated calculations without changing them. For a simple basis function model, separate 4 categories. The observed inputs and outputs come from data. The candidate basis functions are selected as part of the model design. The weights are unknown parameters to determine. Predictions are generated after the representation and weights are applied. In broader modeling methods, transformations may contain adaptable quantities too. For this lesson, we choose the candidate basis functions and treat the weights as unknown. This careful accounting prevents us from confusing observations with predictions or chosen structure with inferred parameters. The same observations can be considered under a linear, quadratic, cubic, periodic, or localized model family. Each family permits different shapes, different behavior between recorded points, and different extrapolation outside the observed range. A more complicated family is not automatically more appropriate. Model structure is a substantive assumption. Data help choose parameters inside that structure, but cannot remove the need to decide what kinds of relationships are reasonable for the problem. An ordinary vector can be assembled from basic directions. The vector 3, 2 equals 3 times the horizontal unit direction plus 2 times the vertical unit direction. A function can be assembled from selected basic shapes in an analogous way. Constant, line, and parabola components can be scaled and added to produce a final curve. This is an analogy rather than a literal picture of the infinite collection of all functions. For a finite selected collection, mathematically advanced learners may say that the basis functions span a finite dimensional function space. The weighted building block idea already appears in Taylor series. Near a point A, a sufficiently well-behaved known function can be represented or approximated using the building blocks 1, x minus a squared, and higher powers. The corresponding weights come from the function value and derivatives at a divided by factorial terms. A function is analytic near a point when it can be represented there by a convergent power series. Merely having a written formula does not automatically guarantee analyticity. For this introductory comparison, the key point is structural. Polynomial building blocks are multiplied by coefficients and added. For e to the x around 0, the series begins 1 plus x squared over 2 factorial plus x cubed over 3 factorial. Start with the constant approximation 1. Add x to obtain a tangent line approximation. Add x squared over 2, then x cubed over 6. Near 0, the curve follows e to the x increasingly well. Expanding the viewing range reveals an important limitation. A low-order local approximation may become poor far from the expansion point. The successive curves make the weighted polynomial structure visible. Taylor expansion and data modeling share a weighted basis structure, but they are not the same method. In the Taylor case, the function is known and derivatives determine the coefficients, usually for behavior near a chosen point. In data modeling, the true relationship is unknown, observations are available, and parameter values must be inferred under a selected model family. Knowledge check 8 asks where the coefficients come from. Taylor coefficients come from derivatives of a known function. Model weights come from observations through an estimation method, which we have not yet developed. Fourier series provides a second major analogy. Suitable periodic functions can be assembled from a constant, cosine waves, and sine waves at discrete harmonic frequencies. Consider f of x equals 3 plus 2 sine x plus 1/2 cosine 2x. First, draw the constant baseline 3, add the slower sine wave with amplitude 2, add the faster cosine wave with amplitude 1/2. The final periodic curve is their pointwise sum. Each coefficient controls the contribution of one harmonic building block. For a known periodic function, Fourier series coefficients may be calculated through integrals. For sampled periodic behavior, coefficients of selected sine and cosine features may instead be estimated from observations. The resulting data model has the same weighted basis form as our earlier examples. A Fourier series uses discrete harmonics to represent a periodic function. A Fourier transform is a related but different construction involving a continuum of frequencies under suitable conditions. We use the series here because it maps directly to a sum of basis functions. Place the four representations side by side. A polynomial data model uses powers of x and estimates weights from observations. A Taylor expansion uses powers around a point and derivatives of a known function. A Fourier series uses sinusoidal harmonics with coefficients obtained from integrals for a known function or estimated from sampled data. The general basis model uses selected building blocks, phi sub j, and weights w sub j. Their shared pattern is function equals a sum of coefficient times building block function. Their assumptions, coefficient generating methods, and typical interpretations remain different. We can now climb the complete equation ladder. Begin with one input and a straight line. Extend to several raw inputs. Replace raw inputs by selected transformed features. Summarize the weighted sum as W transpose phi of x. Stack many transformed observations into capital Phi, giving the prediction vector capital Phi W. Each compact expression is the natural compression of calculations already performed numerically and graphically. Watch the complete pipeline. A scalar input moves along a number line. It passes through several transformations: 1, x, x squared, and sine x. Their outputs become a feature representation. Weight controls scale each coordinate. The weighted values are added to produce y hat. Repeat this process for many inputs, and the outputs trace a complete prediction curve. Stack the feature representations as rows, and they form the design matrix capital Phi. The same weight vector produces all predictions. This is the central mental model: input, representation, weighted combination, prediction. Before closing, test the structure in your own words. What does y equals f of x mean? How does an observed y sub I differ from a predicted y hat sub I? What are the parameters in a line? How does a model family differ from one particular model? Why can two distinct input observations determine one line, while finite observations still permit many functions overall? What does W transpose X calculate? What does a design matrix row represent, and what does a column represent? How can a curved function remain linear in its parameters? Finally, interpret the general sum. Phi sub j constructs building block j, W sub j controls its contribution, and the contributions combine into a prediction. We began with a familiar idea. A known relationship turns an input into an output. We then reversed the problem. Observations were available, but the relationship and its parameters were not. We learned to distinguish observations from predictions, a model family from one selected model, inputs from shared parameters, and raw variables from transformed features. Vectors and matrices compressed calculations without changing their meaning. Basis functions revealed a unifying structure connecting data models, Taylor expansions, and Fourier series. Complex relationships can be represented or approximated by weighted combinations of simpler functions. One central question remains unanswered. When many observations do not lie exactly on the selected model, how should suitable parameter values be determined systematically? That question begins Lesson 2.